presenter is Alexandre Dias from Chemistry Institute from USP, Brazil. And Alexandre, he will be talking about the role of excitons in 2D transition method, dichalcogenides for photovoltaic applications. Transition methods.
Okay.
Sorry.
Hi, thanks for the introduction. Basically, I will talk about the role of excitons in those 2D transition method dichalcogenides for photovoltaic applications. So the main idea, first we can introduce what is transition method dichalcogenides. So basically, these systems are a composition of MX2 formula, okay, where M is a transition metal. Basically, in our work, we use one of those here, okay. We use all of them here in this figure, okay. And we combine this with two chalcogenides, basically of the same species, of course, or sulfur, selenium, or tellurium. Those systems can be encountered in nature in the phase 2A, 1T, 1', and 1TD. Okay, but in this work, as we are interested in the semiconductors for photovoltaic applications, we only focus on 2A phase, that the majority of those systems are semiconductors, okay? But we can need to understand what is the role of TMDs in photovoltaic applications first. So first, these materials are very abundant in nature, okay? So it's easy to, not easier to produce, but you can find it a lot. They are components of third generation solar cells, the most advanced generation of solar cells. They have a lower cost per square meter to produce the solar cell, so that's important, okay? They have achievable power conversion efficiency for solar harvesting, around 20% when we use type 2 heterojunctions, okay? Their optical properties are in the visible spectrum, basically the region where the sun emits its light, okay? So that's important. And they show a dynamical stability at higher temperatures. So we won't have those problems of degradation or transition phase that we can see in perovskites, for example. So as I explained the TMD in photovoltaics, other point that's important is why we can study this, study excitons for those systems. Basically, as I want to apply those systems for photovoltaics, the role of optical band gap is very important. And what happens is that excitonic effects are very intense in those systems, in a way that the electronic band gap is a value and the optical band gap due to excitonic effects is lower than this electronic band gap. So to have a correct description and characterization of those systems, excitons are a fundamental property to analyze, basically. This can be seen in this figure here when I put the absorption spectrum in red with excitonic effects and the absorption spectrum without excitonic effects in blue. So you can see that we have a huge change of the optical band gap here from 2.2 from something close to 1.9 electron volts. So this can change the efficiency of the solar cell, basically. Okay. Our theoretical framework, basically, we start from exciton Hamiltonian, okay? That's basically the electron Hamiltonian combined with the hole Hamiltonian with a 2D potential. It's a Coulomb potential that binds electron and holes. Okay, our excitonic-based function is only a linear combination of all possible electron-hole pairs, as the Q, the exciton momentum, is basically the difference between the Brillouin zone localization of those electronic and hole states, basically this. When we get this base function and write this Hamiltonian in the subspace, it will lead us to Beth-Salpeter equation. So basically, Beth-Salpeter equation is the equation to discover the exciton energies. Okay, so when we solve this equation, basically we can obtain that spectrum that I showed in the previous slides. So normally, we can solve this equation in two pictures. The first is the traditional ab initio picture. Okay, so we start with this function theory. You can choose LDA or GGA approximation. You can obtain the constant states and the electrical density. we will correct the band gap with cause particle correction, GW, okay, and solve this Beth-Salpeter equation with some ab initio code. We have some computational implementations of this, as VASP, YAML, Beckley GW, exciting. They are very good codes. The problem of this picture, the computational cost is very higher. So if you look literature now, you only see works perform this calculation for smaller systems with around 4 or 5 atoms. And that's a problem, as a lot of crystals can't be represented with so few atoms. In Ketanano group, we try to solve this equation by a different way. So what we do, we start from the same point, dense function theory, okay? But what we do different is we get this electron density and we can generate a Hamiltonian, a type binary Hamiltonian using Wannier functions. This was done using the software called Wannier 9. And it will deliver some Hamiltonian that we can use instead of get the state from dense function theory. In this description, basically we can solve the same Beth-Salpeter equation, but it's more easily to solve this, and basically the computational cost is lower. Okay, but if you can think, okay, but which computational implementation do you have to do this? In the market, you have none to do this. The question is, we are developing one computational tool to do this, to solve this equation, as we call this anti-Bexus code. This code, with this code, we had 2 publications, okay, 2 papers published. One about these results about 2D materials, and other one about perovskites. And we have one submitted paper that when we study another kind of perovskites to see excitonic effects. Okay. The main difference of our code is, as we are using maximum localized Wannier functions, the computational cost is lower, and we can work with systems with a larger systems. Sorry. So in this submit paper, we can work with 50 atoms, which is 10 times higher than the systems that people today are solving with ab initio picture. So basically, this is one of our main advantages. Of course, we can also keep a good precision in our results. This work of TMDs, basically what we do is we start off 72 monolayers, okay? Basically perform some phonon calculations to separate the stables from non-stable systems. As you can see in this picture in the middle, okay? And have only 14 stable systems, okay? Stable semiconductor are 14 from those 72 by phonon calculations. We identify which one are semiconductor or metal. Basically, we are interested only in the semiconductors. After this, for the semiconductors, we correct the band gap, use some hybrid dense functional theory, okay? And with those results, we can perform the maximum localized Wannier functions, obtain our tight binding model, and our tight binding results are shown in this right part of the slide here, okay? When we show MOS2 and WS2, and we can achieve a very good description of the electronic properties with this methodology. And with this tight binding model, we can solve the Beth-Salpeter equation, calculate the excitonic properties, perform the type 2 heterojunctions, and see if those heterojunctions with 2 different monolayers are good or not for solar harvest. Okay, so basically this slide will show some optical properties that we calculated with our code. So the left picture here, basically we can try to see in the first Brillouin zone which K point are optically achieved, okay? And you observe that when I start from group 4, 5, and 6, basically the most interesting system are the group 6, okay? And we have basically the optical activity in the K or K prime value. Then what we see here, we do here, you can change the light polarization. You can choose which value you can activate, basically. This is important for other applications, not for photovoltaics, but it's interesting to see this physical phenomena and see that our description can provide this, as these are widely reported in literature, okay? In the right figure here, we calculate the absorption spectrum here, okay, with and without excitonic effects, in order to show how it are important in the description of the optical band gap of those systems. In these D, E, and F figures, basically change the light polarization and see if it has some effects in the absorption. So basically for the titanium and molybdenum, the effects are not so much bigger, but for vanadium disulfide, the effects are quite interesting because you can have some explicit selection here of the values, okay? And those two values has different energy. But this is not the main subject of this presentation. But basically this property is good because you can tune the optical band gap, change the light polarization. So sometimes you can use some polarize in your solar cell and can achieve a better energy harvesting efficiency. So, but power conversion efficiency, in this work, we use a very simple model, okay? We have something more sophisticated later, of course, but sometimes the simple is the best. Basically, you can have a description that solves our problem. So the main idea here is to use a TMD type 2 heterojunction here, okay, as a photoabsorber component of our solar cell. So basically, the power conversion efficiency are calculating the Shockley case limit, where we assume that all photons that are in the solar cell are absorbed, basically. So we don't worry about some kind of, okay, I put the light and it absorbs only 20% of light. No, we are assuming that if we can absorb all light, we can obtain this power conversion efficiency. Of course, sometimes it's not very realistic, okay, but we can have some strategies to achieve these limits. Basically, we can use some mirrors, can use some light trapping schemes, okay. So we try to show this work the maximum efficiency that we can achieve with those systems. And of course, we are interested in type 2 heterojunctions, okay, in this. And to see which kind of the heterojunction is formed here, basically can make some kind of band alignment here, okay, using the reference as a vacuum level. And it's interesting because we perform this with and without excitonic effects. So we use electronic band gap and optical band gap as being the optical band gap obtained with excitonic effects. Notice even if the correction is smaller, it can change the kind of band alignment of the systems, as you can see in this figure here, okay, where you have the blue color to identify the type 2 heterojunctions. But sometimes when you have the blue and red in the same, what you see is you have type 1 heterojunction if you use electronic band gap or optical band gap. And for the other kind of band gap, you can change for type 1-2 or type 1-3 or 2-3, basically this, okay. In this table here, I put the power conversion efficiency of those systems, and I highlight here as a green the ones that the heterojunction that has a higher power conversion efficiency, basically. So what we observe that is the most interesting system for solar harvesting is the one formed with group 6 transition metals. So we studied from group 4 until group 10 or 11. But for this application, basically it has some lowering of power conversion efficiency. Okay, this is without excitons, this is with excitons. For some others, we have some enhancements. What we see is that this contribution could be important. Of course, sometimes you can do this, but you can have some insights of how it changes.
Minuto, Alexandre, por favor.
Lowering of power conversion efficiency. Okay, this is without excitons, this is with excitons. For some others, we have some enhancements. What we see is that this contribution could be important. Of course, sometimes you can do this, but you can have some insights of how it changes.
Minuto, Alexandre, por favor.
The main importance of excitonic effects, basically, as different from the electronic band gap, we can control the exciton binding energy, or we can define this as a difference between the optical band gap and the excitonic, the electronic band gap and the optical band gap by excitons, controls the kind of dielectric environment around our monolayer. So that's important because when we control this, we can change this exciton binding energy, which is the same thing to control the optical bandgap. So we can use some substrates as a strategy to enhance the efficiency of our monolayers. Basically, this is the main reason that we can control excitonic effects in substrate, and something that you cannot do if the system hasn't excitons, basically. Okay, here this slide I only talk about our code that we are developing. It has several functionalities here, okay? But this code could be used to calculate excitonic effects, but can also some electronic properties and back curvature, basically. But we can talk about this code in another presentation in the future. So what we can conclude from this presentation, basically start with a large group of monolayers, but only a few, 14, are suitable for photovoltaic applications, okay? Our description using Wannier functions are quite good, okay, when compared with DFT results. The excitonic effects are important in these systems, and you can modulate the exciton binding energy, controlling the dielectric environment. So basically, if you control the dielectric environment, you can control everything about this material. This is important because you can enhance the power conversion efficiency of those heterojunctions. Okay. And finally, what we try to propose here is a different way to calculate those effects using our computational tool, one-time-axis code, that we expect to publish next year. Okay. And this could make easier the study of excitonic effects in solids with this alternative methodology. Basically, is this. Thank you.
Okay, Alexandre, thank you very much for your talk. Excitonic effects are very important for all sorts of applications. We understand in nanomaterials, 2D materials, they are very important. So we are open for questions. Anybody? In the Q&A, in the chat.
Yes,
Ana Flávia. Yes, Ana Flávia, please.
Alexandre, I have a question. With a predicted efficiency of 20% for this TMD, what's the challenge to see then this heterojunction actually in a practical device? I know that I'm asking you a very experimental question, but I think it's really important about the current state of art for this kind of TMD in PV.
Okay, basically the challenge today is as those bilayers are very thin, they won't absorb 100% of the light. Okay, so basically they absorb about 20%, maybe less. So if you consider 20%, of course we won't achieve this 20% of solar harvest efficiency. So now what we need to try to do is build a way to enhance this absorbance from 20% to 100%, 9%. It's reported in literature some that talk about this. Basically, they put some mirror, they tried something to trap in the light, but they doesn't show some specific details, of exactly how to do it. So this could be challenging in the experimental point of view. Okay, because if you only consider this 20% absorption, of course the performance will be very lower than what I presented here.
Can you make them, instead of like a thin layer, can you make them as a bulk? What happens with the efficiency when you have a bulk material? Like, I mean, like very thick layers of these materials. What about
I have a transition from direct to indirect bandgap, okay? This indirect bandgap allows some kind of recombination that will lower the performance. If the difference between direct bandgap and indirect bandgap, the performance could be very lowered. Basically, it depends, of course, the energy difference of those transitions. So this is a problem when we try to go to a bulk. Of course, when we go to a bulk, the excitonic effects are very smaller, okay? And of course, you have some lowering of the bandgap, so it will cost you the performance, basically. Layers or heterojunctions.
Yeah, but we cannot forget that silicon is a direct band gap. Silicon is a direct band gap, and this is the technology that is in the market. So I believe that there are many other issues here on a case for these bulk materials. I mean, not the thin layer, because the thin layers are other stories, because if you're only absorbing like less than 10%, your photocurrent is going to be really, really small. But thank you. Very interesting talk.
Just want to add, there are some chalcogenides, not this type of TMDs, but antimonium selenide has very high efficiency, like not 20%, but they are up to 80 or 9%. I don't know if you're familiar with that, Alexandre. That's a material that is a very interesting family to study. So for tin sulfide and antimonium selenide, people are studying these materials. So they're a little different, but they are both.
What happened in the past? We try to prepare. What happened in the past? We try to prepare some. It was a long time ago. It was we are working with dye-sensitized solar cells, and we decided to use this TMD in the form of thin layers, very few layers, as a counter electrode in dye-sensitized solar cells. And the problem that you had at that moment was because of the stability, because it was very easy to oxidize these very thin layers, and then even working inside of the glove box, I remember it was really hard work. And we had a problem with the stability. Oxidation, it was something that was like destroying our, in that time it was using as a counter electrode.
There is another question, more technical. Dear Alexandre from Israel Ribeiro, thank you so much for your talk. I'd like to know, in the tight binding model, how should I sample the K point grid taking into account the time reversal symmetry?
Okay, this time reversal symmetry, sometimes it has some systems or not, it doesn't, in other doesn't have, okay? So basically this is more important to describe some kind of spintronic properties of those TMDs, but not photovoltaics, okay? Basically, this is related with the configuration of spin. When I go to K point for minus K, you can have some spin flip in the valleys, okay? But this doesn't happen for group 4, for example. This only happens with group 6. And you can see something similar in group 5, but is different. This time reverse symmetry, okay? So what I can say is basically to calculate those optical properties for photovoltaic applications, that's not significant if you worry about this or not. But they can be used this property for spectronics or something related with quantum computation, basically.